What specific problem does your proposed method of self-reflection aim to solve in the context of large language models, LLMs? Can you elaborate on the limitations of existing approaches that your method addresses?
The proposed method of self-reflection aims to solve the problem of improving the performance of large language models, LLMs, on tasks where they initially fail, by enabling them to analyze their reasoning and correct mistakes through self-reflection. Existing approaches, such as prompting for self-reflection, often struggle with limitations like the inability to reliably identify errors without ground truth oracles, diminishing returns from repeated reflection, and the risk of performance deterioration on easier prompts or high-performing models. Our method specifically addresses these limitations by employing a reinforcement learning strategy, Group Relative Policy Optimization, GRPO, which rewards effective self-reflections based solely on binary success-failure feedback, thus optimizing the model's ability to self-reflect without requiring additional task-specific data. This approach allows for task-agnostic improvements, ensuring that the model learns to enhance its self-reflection capabilities across various tasks rather than specializing in one. Ultimately, our method demonstrates that optimizing for self-reflection can lead to significant performance gains, even surpassing larger models that do not utilize this technique.
How does the proposed method or algorithm work? Please illustrate it step by step, detailing the underlying processes from initial response generation to the application of reinforcement learning.
The proposed method, termed Reflect, Retry, Reward, operates in a systematic manner to enhance the self-reflection capabilities of large language models, LLMs. Initially, the model is prompted to complete a task. If it succeeds, no further action is taken. However, if the model fails, it generates a self-reflection analyzing its reasoning flaws. This self-reflection is then utilized in a second attempt to complete the task. If the second attempt is successful, the Group Relative Policy Optimization, GRPO, reinforcement learning algorithm is applied, rewarding only the tokens generated during the self-reflection, thereby optimizing the model's ability to self-reflect effectively for future tasks. This process allows the model to learn from its mistakes without requiring additional task-specific data, focusing solely on improving its self-reflection skills.
Can you provide a simple yet illustrative example to demonstrate the inner workings of the Reflect, Retry, Reward methodology? Walk through the main steps of the algorithm using a hypothetical example.
The Reflect, Retry, Reward methodology operates through a structured process that enhances a model's performance after it initially fails at a task. For instance, suppose a model is tasked with generating a function call based on a user query but fails to produce the correct output. First, the model generates a self-reflection, analyzing what went wrong in its initial attempt. Next, it uses this self-reflection to make a second attempt at the task. If this second attempt is successful, the model is rewarded using Group Relative Policy Optimization, GRPO, specifically by rewarding only the tokens generated during the self-reflection, thereby reinforcing effective self-reflective behavior for future tasks. This process allows the model to learn from its mistakes without requiring additional task-specific data, optimizing its self-reflection capabilities for improved performance across various tasks.
What are the theoretical or practical benefits of using Group Relative Policy Optimization, GRPO, for training self-reflection in LLMs? How does it compare to traditional reinforcement learning methods like PPO?
The theoretical benefits of using Group Relative Policy Optimization, GRPO, for training self-reflection in LLMs include its ability to directly estimate advantages by comparing outcomes from a group of sampled completions, which is particularly useful in environments with sparse supervision. This contrasts with traditional methods like Proximal Policy Optimization, PPO, which rely on a separate value, critic network, making GRPO more efficient in scenarios where feedback is only available at the end of a generation. Practically, GRPO encourages models to persist through failure by rewarding retries after unsuccessful attempts, promoting self-correction and robustness. Additionally, GRPO allows for a task-agnostic approach as it optimizes self-reflection without requiring task-specific data, thus enhancing the model's general reasoning capabilities. Overall, GRPO's design makes it well-suited for complex tasks where immediate feedback is not available, leading to improved performance in self-reflection training compared to traditional reinforcement learning methods.
How did you validate or test the effectiveness of your self-reflection training approach? What datasets and performance metrics were used in your experimental design?
To validate the effectiveness of our self-reflection training approach, we conducted experiments using two specific datasets: the API-Gen dataset for function calling tasks and the Countdown dataset for math equations. We evaluated model performance based on the success of their first and second attempts at completing tasks, measuring improvements in accuracy after self-reflection and reinforcement learning training. Performance metrics included the percentage increase in correct responses after the second attempt using self-reflection, with results showing an average improvement of 4.5% for API-Gen and 5.3% for Countdown before GRPO training, and further increases of 4.7% and 8.6% respectively after training. Additionally, we ensured the integrity of our experiments by only evaluating models that were released prior to the datasets, thus preventing any unfair advantage. Overall, our experimental design focused on binary success-failure validation through task-specific verifiers, allowing us to assess the impact of self-reflection on model performance effectively.
What specific results did your experiments yield regarding model performance improvements? Can you summarize the gains observed during the API-Gen and Countdown tasks after applying your self-reflection method?
In our experiments, we observed notable performance improvements in both the API-Gen and Countdown tasks after applying our self-reflection method. For the API-Gen task, models showed an average performance increase of 4.5% after a second attempt using self-reflection and a further 4.7% improvement post-GRPO training, allowing models to outperform even larger models like Qwen 2-72b after just one attempt. In the Countdown task, self-reflection led to an average performance increase of 5.3% before GRPO training and 8.6% after, indicating that models starting from a lower baseline had greater opportunities to learn. Overall, our findings reinforce the effectiveness of self-reflection in enhancing model performance across diverse tasks.